So I hope you're happy with what you do when you have one stereogenic carbon. You can look at it, you can sign whether it's R or S, and you know how it's going to be affecting the rotation of plane polarized light. Where it gets more fun is when you have more than one stereogenic carbon in a molecule. Because if you've got two possible enantiomers for each carbon, and then you've got two stereogenic carbons, then in theory you've now got 2 times 2 or 4 possible stereoisomers. Now, as we'll see on this slide and then the next slide, sometimes that's true, sometimes that's an extra little subtlety that you have to be aware of. But anyway, let's dive in with this molecule, shall we? Okay, if we look at those two carbons there, the one on the left has got an OH, a methyl, a hydrogen, and then this big blob here, and the one on the right has got an NH2, a COOH, an H, and then this big blob here. This, by the way, is an example of an amino acid. Now let's look at it and let's assign R and S, shall we? So in order to do that, we need to think about priorities. Left-hand carbon, obviously, the oxygen is the first thing, but then we've got it bonded to a carbon, and a hydrogen. Well, I hope you would obviously see that this carbon here goes to a nitrogen, a carbon, and a hydrogen. This carbon here just goes to paltry 3 hydrogens. So therefore, as far as the left-hand carbon is concerned, this is priority 1, this is priority 2, that is priority 3, and of course the hydrogen is priority 4. So the gold numbers are associated with the priority for the left-hand carbon. Now let's look at the right-hand carbon. Obviously, the right-hand carbon goes to a nitrogen, so that's its top priority. Notice I'm using fuchsia-colored numbers here. Now let's look at the other things that this carbon is bonded to. It's bonded to a carbon here and it's bonded to a carbon there. Which one of those is better? Well, that carbon goes to an O, a C, and an H. This carbon goes to OOO, because remember it's an OH for that's 1 oxygen, and C double bond O for 2 and 3 more oxygens. So that means that this gets the fuchsia 2 and this one over here gets the fuchsia 3. Okay, so there are the priorities that we're going to use as we look at the actual molecules themselves. So here is a molecule right there. Okay, and there is its mirror image. Let's make sure you're happy how I'm doing the mirror images, right? You've got the two carbons, the stereogenic carbons that are there. What was on the left is now on the top. What was on the right is now on the bottom. And now we mirror image it over there. So there's the OH matched to the OH, the amine to the amine, the acid to the acid, the methyl to the methyl, and I've stuck both hydrogens to the back just to make it a little bit easier to assign RNS. So have a look and tell me, or tell yourselves, because I can't hear you, what this carbon here is. And I hope you said that it is R, because you've got, there's priority 1, priority 2, priority 3. How about this one here? S, you said. Shame, because it's R. Let's again look, priority 1, priority 2, priority 3. So this is RR. In theory, this is its mirror image. It's an enantiomer, and of course, when you have a mirror image, R goes to S. Let's see if it really does. This carbon here, priority 1, priority 2, priority 3. We're going counterclockwise. How about the bottom carbon? That was the fuchsia carbon. Priority 1, priority 2, priority 3. Again, we're going anti-clockwise. So there we are. We got those two possibilities, RR and SS, that are enantiomers. Now let's look at their physical properties. As they're enantiomers, they have the same melting point, the same boiling point, pretty much the same reactivity. Where they differ is in how they rotate plane polarized light. So this one here, the RR, rotates light 28 degrees negative direction, which is actually to the left. And the enantiomer, SS, rotates the light 28 degrees to the right. So you can tell they're enantiomers, same melting points, opposite rotations. Now let's look at this molecule here. First of all, I want you to agree that this is neither that molecule nor that molecule. The top part here is got the OH, H at the back, and then a methyl, just like this top carbon here, which makes that an R, okay? But this bottom one here now has the NH2 priority 1, then priority 2, then priority 3. So that bottom one is S. So this molecule was RR, this one was SS, this is now a new one, RS. And I drew its mirror image, and again, please make sure you see the mirror image part there, OH to OH, COOH, COH, amine to amine, methyl to methyl, and hydrogens at the back again. Okay, so if this is the enantiomer of that, that means that this must be S, is it? Yes. And the bottom one must be R, is it? Yes. 1, 2, 3, going clockwise. Okay, so these are enantiomers of each other, but if we look at their properties, this one melts at 274 degrees Celsius, different from that one. Okay, this one I'm going to predict therefore melts at 274. This one, the RS, rotates light of -9, so I'm going to predict that this one here, its enantiomer, rotates light at +9. And look at that, I was right, which I should be as I know when I wrote the bleeding slides, but it is actually correct. Okay, now the relationship between these two are enantiomers. The relationship between these two are enantiomers. What's this other relationship? Okay, these are stereoisomers, right? They've got the same atoms bonded to each other. Okay, so therefore they're not structural isomers where you've got different atoms bonded to different atoms, right? These are the same atom bonding, the same connectivity, but they're obviously not the same molecule. So that relationship now is they are called diastereomers. Okay, D-I-A-S-T-E-R-E-O, mers. Okay, so going back to our original point, we've got two stereogenic carbons. This can be RS, this can be RS, so you have two pairs. RR is an enantiomer of SS, RS is an enantiomer of SR, and the relationship between RR and SS and RS and SR are they are diastereomers. Let's look at another one. This molecule here, okay, really pretty molecule, a couple of acids, a couple of alcohols. Let's quickly go ahead and assign priorities. On the left hand side, we've got gold 1, this carbon OCH, this carbon of course 3 oxygens, so therefore that's 2, and this one over here is 3. Let's go to the fuchsia. Again, the OH is going to be 1, the COOH is going to be 2, and this residual bit is going to be 3. Okay, so now let's look at a particular possible molecule of that. So here we are, COH, OH, OH, COH. Let's draw its enantiomer. There is the mirror image, it's an enantiomer. They're not going to be superimposable, one will assume, as they are enantiomers with two thingies in there. Let's check that though. Top carbon here is going to be 1, 2, 3, so therefore it's going to be R, and the bottom one here is 1, 2, 3. It will also be R. Okay, this one over here, OH 2, 3, so that's S. Here we got OH acid group, also S. Yes, they are enantiomers and they are different because you've got the RR and the SS. Okay, now let's draw another version of that. Okay, so here I'm keeping the top part here and I'm going to use the bottom part there. There is its enantiomer. So this one is R, that one is S, and therefore S and R. Cool. Now, I kind of skipped over because I forgot the order I was doing the slide, but never mind. For these two here, same melting points, 172. This one rotates at +12, so this one rotates at -12. All well and good. These are enantiomers. These ones here, of course, should be diastereomers, shouldn't they? So therefore, they should have a different melting point. And indeed, this one melts at 165 different. But oh, holy poop, look at that. It's got 0 rotation. And when I look over here at this molecule, it's also got a melting point of 165 and 0 rotation because R went to S, S went to R. But if you look at how I've drawn the molecule here, you can see that there's actually the possibility of a symmetrical plane in there. If we look at how I've drawn this here, there is a symmetrical plane there, where if you just draw it there, COH, COH, H, OH, OH, H, H, and so on. right? What I've tried to show by reproducing this over here, yes, they're enantiomers, but they are actually the same molecule, okay? When you've got two molecules that are mirror images, but they're actually the same molecule, okay? Well, then these are called a meso compound. Meso compound is where you have two or more stereogenic carbons, okay, but they are mirror images of each other. So when you've got the carbon here and this carbon here that have the identical groups on each other, because that's what you got to have, the identical groups, then when one is R, one is S, it's the same thing as S and R, because all you have to do is take this molecule and flip it around and you get that molecule. RR and SS, no problem, they're enantiomers, but this molecule here has got three stereoisomers, the RR, the SS, the enantiomers, and then the meso compound. I hope that kind of makes sense. I was sort of a little bit tongue-tied through it, but we can talk about it in class, should you wish. The last little example we're going to do, and we'll expand upon one of these as we're going through in class, but are some special cases. And for this, again, I want you with your model kits. Here is a molecule called allene. Okay, this one here is a dimethylalene. Okay, and there's no stereogenic center here because this carbon has got just three things on it. This carbon's got three things on it. Okay. But if I make the mirror image of this, it is non-superimposable. Try it. So these are enantiomers, even though they have no stereogenic center. Another case that we've talked about quite a bit in terms, first of all, of isomers, and then we're also going to talk about it in terms of conformations, are rings. And so now let's again think of our 1,2-dimethyl cyclohexane. Okay, this is the cis isomer in which both methyl groups are on the same side of the ring. Okay, there is a mirror plane therefore that runs through this molecule when I've drawn it like that, and so it's meso. This carbon is stereogenic, this carbon is stereogenic, but they're the mirror images of each other, so it's meso. Conversely, the trans, so now we've got one coming out and one going away from you. If I draw its mirror image, okay, again, stereogenic carbons all over the place, but this is now non-superimposable. If we go ahead and so if I took this and tried to rotate it round so it matches up a little bit more, you can see it's just not going to match up. It's worth assigning R and S to these things. There is the S and the R. Again, if this is S and it's a meso compound, this had to be R. With the trans, we're going to get the RR and the SS. Make those models, look at them. Make sure, first of all, that you cannot superimpose the allenes, and then also have a look at these. Make sure that you can see why this is RR, this is SS. These are non-superimposable. However, try and make the mirror image of this, and you'll see it's the same molecule, a meso molecule. See you in class.